Welcome back. Recall that in the previous lecture we were constructing Green's function for linear second order boundary value problems. So, let me recall what we are trying to do. So, this second order equation d by dt of pt dy by dt plus qt equal to f of t in the interval a b, and we have taken the boundary conditions y a equal to y b equal to 0. So, p is a continuously differentiable function and a positive function in the interval a b, q and f are continuous functions. So, let me recall the procedure we adopted to construct the Green function. So, we started with W1, W2, two linearly independent solutions of the homogeneous equation. So, that is f is identically 0 and W1 a equal to 0. So, one of them satisfies boundary condition at one end and other one at other point a b. Okay. So, we also normalized W and W2, so that the Wronskian of W1 W2 is equal to 1 by Pt. Okay. Under these conditions, the Green function of the boundary value problem was defined by this expression W1 S W2 T if A is less than or equal to S less than or equal to T and other way around if S if T is less than S less than or equal to P. Okay. And the solution, required solution for the boundary value problem was the solution y t is given by this integral a to b g t s f s t s, and we verified that this y given by this integral satisfies both the boundary conditions as well as the differential equation. Okay. So, we will illustrate this one through an example, simple example. So, example very simple one. So, y double dot minus y is equal to f t. So, in the interval 0 less than t less than 1, and again I take the boundary conditions as so y vanishing at both the endpoints 0 and 1. So, in this so this is a second order equation with constant coefficients. So, if you study the homogeneous equation, so E exponential t exponential minus t are linearly independent solutions of the homogeneous equation. Okay. And we have to construct two linearly independent solutions satisfying boundary conditions at different points. And if you just look at the boundary condition here, so you just W1 t, which is a linear combination of e to the t and e to the minus t, and we want that to vanish at 0. So, one that easily found is sinh t. So, this is sine hyperbolic t. So, let me just you all know this thing, but let me just write that. Okay. And you see that W10 is 0. Okay. So, that is a solution of the homogeneous equation and it satisfies this boundary condition. And similarly, at t equal to 1, you just see that this fellow will do 1 minus t. So, again when you expand this, this is a linear combination of e to the t and e to the minus t, hence it is a solution of the homogeneous equation, and at t equal to 1 this is 0, t equal to 1. Okay. So, now let us check whether that normalized or not. So, let us compute the Wronskian. So, Wronskian. Okay. So, you just W1 t W two dot t minus W1 dot t and W2 t. So, if you use these expressions and write the derivative, this is simply minus C1 C2, and you use addition formula for the hyperbolic sine function, what you find is sinh 1. So, that is a constant. So, choose, because we want this to be 1, Wronskian to be 1 by p t, and p is 1 identically 1 here. So, choose C1 C2 such that C1 C2 is equal to minus 1 divided by sinh 1, sine hyperbolic 1, and then the Green function in this case. So, G T S is minus sinh S sinh 1 minus t by this normalizing thing sinh 1 if 0 less than s less than or equal to t, and minus sinh t into sin hyperbolic 1 minus s divided by if t is less than s less than or equal to 1, and the solution is just simply y t is equal to 0 to t 0 to 1 g of t s f of s d s. So, if you take a particular f, for example, if for example f is identically equal to 1, so we can integrate this easily, we find, and so you can easily check that y t is equal to. So, let me write that 1 minus e to the minus 1 divided by e minus e to the minus 1. This is coming from sinh 1. So, e to the t plus e minus 1 by e minus 1 e to the minus t, and there is a minus 1. Okay. So, you can verify this. So, this satisfies the equation y double dot minus y equal to 1 with boundary conditions y 0 equal to y 1 equal to 0. Okay. So, as I remarked earlier, so if we again change the boundary conditions, okay, the solutions W 1 W 2 they change, and accordingly the green function changes. So, green function is very much dependent not only on the equation, but also on the boundary conditions. So, that you should keep in mind, and we have a nice recipe in this case to construct the solutions of the boundary value problem via the green function. Okay. So, we will discuss the uniqueness little later. So, we have found a solution. The next question obviously is that whether it is unique or not. Okay. So, now we go to general second order equations. Order equations and see how far we can carry whatever we have done in linear case. So, second order linear equation. So, let second order general equation. So, I consider this non-linear equation. So, y double dot equal to f of t y dot. So, again this is in the interval a less than t less than b, and now I take general linear boundary conditions. Okay. So, not able to do much with general boundary conditions. We consider so boundary conditions B C. Okay. So, a 0 y a minus a 1. So, there is no particular reason why I take minus, but can also put plus, no problem. So, a 1 y dot a is equal to alpha and b 0 y b plus b 1 y dot b is equal to beta. So, in the previous case what we had was a 0 equal to 1 and a 1 equal to 0 and alpha equal to 0, and similarly b 0 equal to 1, b 1 equal to 0 and beta is 0. Okay. So, only the condition is that this a 0 a 1 should not vanish simultaneously. So, that we will put here. And similarly, the other condition. So, they do not vanish simultaneously, one of them can be 0, fine, and alpha beta are again given real numbers. Okay. So, now we will discuss this. So, let me again put some numbers here for this. This is 1 A and the boundary conditions 1 B and the whole thing together called problem 1. So, I would like to discuss the existence of a solution to this problem 1. That means, we want a function y to be determined which is 2 times continuously differentiable and satisfies this given differential equation and these boundary conditions at the end points A and B. See, unlike in the linear case, we do not even know how to start, because here there is no concept of the homogeneous equation, because everything is clubbed here. So, I cannot separate the linear part and inhomogeneous part, homogeneous part and inhomogeneous part, and how to start. Okay. So, that is so we are already facing a problem even to start where to start. Okay. A formal approach is the following. So, we start with an initial value problem. Start with an IVP. So, this is BVP. So, this is we want to discuss, and we start with an initial value problem. What is the initial value problem? Equation is the same. So, now I use different unknown function. So, u double dot equal to f of t u dot. Okay. So, this is second order equation, and now I impose conditions only at A. So, I will not bring in B, because we are studying just some initial value problem. So, at one point we give the data. Okay. What is that data? Okay. So, you just A 0 U A which is same as the condition at A in the BVP. Okay. And now I will have another independent condition at A only, C 1 u dot A, I put an S here. Yes, and this S is at my choice. So, this, so S is any real number for the time being. Okay. And these two conditions are linearly independent. Linearly independent. What does that mean? You cannot obtain one condition from the other, and in terms of the coefficients, this means so that means the initial conditions are independent, that is this matrix you have A 0 A 1 A 0 minus A 1 C 0 minus C 1 is non singular. That means you have this A 1 C 0 minus A 0 C 1 not 0. Okay. That is the meaning of that linear the conditions are linearly independent. So, by fixing, so since the second condition is at our choice, by fixing C 0 C 1 we may assume. So, this is kind of normalization, that A 1 C 0 minus A 0 C 1 is equal to 1. Okay. So, then you just forget it, and we have that initial value problem. So, let me just again, so this IVP. Okay. So, this let me call it. So, this is 2A and 2A, 2B. Okay. And suppose IVP has a solution defined for suppose the IVP has a solution defined for A less than or equal to T less than or equal to B. So, you want the solution to exist all the way up to B and perhaps even beyond B, but at least we want up to B. So, here we have to include, we have to impose certain conditions on F to ensure this, like global Lipschitzness and other things. Okay. So, we have now the solution for the, so let me just write again, U double dot equal to F of T U U dot, and we have this A 0 U A minus A 1 U dot A equal to alpha, and C 0 U A minus C 1 U dot A equal to S. S is at our freedom, okay, and we have normalized, so that this A 1 C 0 minus A 0 C 1 is 1. So, these two conditions are linearly independent, and we have a solution which exists for the entire interval A B. Okay. So, to emphasize the dependence on S, so denote the solution by U T, and you stress this S, and S is coming from the second condition we are imposing at A. Okay. And now you form this. So, consider the function phi of S. Now, I defined this function. So, which is B 0 U B. So, U is the solution of the initial value problem. So, remember that, yes, plus B 1 U dot B S minus beta. So, if you remember the second condition, boundary condition, so it is of that form. So, I am just evaluating the solution of the initial value problem at t equal to b. So, this is nothing but the evaluation of the initial value solution of the initial value problem at t equal to b. Okay. And now, this is a purely a function of S, because everything B 0, B and beta and u, now everything is fixed. So, this is just a function free from R to R. Okay. So, now that we have got a function defined from R to R. So, for every S I will have solution to the initial value problem, and once I obtain that solution of the initial value problem, I compute this thing and call it phi of S. Okay. So, now ask the question. So, is there an S star such that phi of S star is 0? That is the question. Okay. So, remember this phi is a function from R to R. So, this is no guarantee that there is a root of that thing. So, in case there is, if yes, then the solution, then the function y t. So, this is the definition. So, u t S star is a solution of BVP. Okay. So, this is, remember, this is solution of IVP. So, this we already know, and certain conditions on the right hand side function f, we always have a solution. At this point, okay, uniqueness and other thing will not discuss. So, just there exists a solution, and in addition to that, if there is an S star satisfying this condition, which is a root of the function phi, then using that solution of the initial value problem, we obtain a solution of the boundary value problem. So, in the literature this is called shooting method, and this is widely used in obtaining numerical solutions of the BVP. So, this is very important method, and same thing can also be used for theoretical purposes as we are studying. Okay. And so, if there are more solutions to this equation, if there are more rows to this phi, then we obtain as many solutions for the boundary value problem. So, in general we cannot say whether there could be no solution, there could be only one solution, there could be multiple solution, and depending on that the boundary value problem will have a solution, a unique solution, or multiple solutions, or no solutions. Okay. So, in order to sum up, so just let me state a theorem So, let me just put that theorem. Okay. So, let R be the region consisting of all triplets T, U1, U2. So, A is less than or equal to T less than or equal to B, and U1, U2 in R. So, this is the region, and assume, so this is our right hand side M F. So, this is a function of T U1 U2 is globally Lipschitz in R. That is, if we take f of t u1 u2 minus f of t v1 v2, this is less than or equal to some m1 u1 minus v1 plus m2 u2 minus v2 for all t u1 u2 t v1 v2 in the region. So, let me not write that for all okay, let me write in R. Okay. So, then BVP has as many solutions as the as many solutions as the roots of the function phi. So, for every root of this function phi, you get a solution of the bound value problem. Okay. So, remember that what phi is. Okay. So, this one, okay, somewhat very strong condition, okay, and that ensures. So, this is just for the ensure that a solution of IVP exists for all t in AB. Okay. So, if you have some other means of ensuring the same thing, we do not need this strong condition. Okay. So, in fact, let me give an example. So, an example. Somewhat difficult integration, but is doable. So, this is again second order equation. So, you let me just write y double dot plus lambda e to the u is equal to 0 in 0 less than t less than 1 and y 0 equal to 0, y 1 equal to 0. Okay. Let us consider this BVP. Okay. So, if you follow this shooting method, so what we should do is this consider the IVP u double dot plus lambda equal to 0 and one initial condition is same as the one coming from the BVP, and second one we want linearly independent. So, it has to be in u dot equal to yes. Okay. S is at our choice. Okay. So, as an exercise, write down the solution in explicitly. So, this can be done. So, there is no problem with that. So, in fact, you can use the conservative nature of the equation. So, you can easily integrate once and you convert that into a first order equation, and then using method of you separate the variables and integrate it. So, it is bit complicated, but doable. Okay. So, you can explicitly solve it, and in the solution you see that the dependence of S very clearly in that. Okay. Now, you next check using that solution. Okay, using that solution, check for which S, for which S, if there is any, it is not guaranteed, if there is any, the solution U also satisfies the other boundary condition, namely U of 1 equal to 0. Okay. And if, and also you check check for the uniqueness, whether there is one S or more S, check for uniqueness. So, it is a good exercise. So, you will see how this shooting method is at work. So, why this example? So, why I want to stress this example is this, in this case this f of t u dot very simple, it is just minus lambda u if you want to write it. Okay. And this is not globally Lipschitz, not globally. Okay. But yet the solution exists for all t in the interval 0 1. So, that is important. Okay. So, there are, I mean that is one wants to state as a theorem, one has to be very stringent. So, maybe you put lots of conditions, but in practice such stringent conditions may not be required. Okay. So, for example, this one. So, even without the assumption of globally Lipschitz, you can write down the solution explicitly, and you see that the solution exists for the entire interval 0 1. Okay. So, this is one example. Okay. And so, let me again continue. That's why this shooting method. Okay. So, what is happening? Shooting method. So, geometric picture. So, here so this is A, this is B. So, for let me just take for example simple thing u A equal to 0, u B equal to 0, just for the illustration. Okay. So, what we are doing is, so starting here, but with a velocity. So, u dot A is equal to S, u dot A is equal to S. Okay. So, we are releasing, we are shooting some particle from here, and it may just go somewhere depending on S at B, and if I choose another S, it may go somewhere. So, would like to determine an S for which we eventually go there. Okay. So, that is why it is called shooting method. So, by changing the initial velocity in this particular setup of boundary conditions, we are looking for a particular velocity with which if we shoot, we are reaching the destination. Okay. namely u b equal to 0. Okay. So, that is the idea. So, that is why it is called shooting method. Okay. So, again let me go back to the analytical description. Okay. So, we started with, let me again go back to y dot equal to f t y dot and a 0 y a b 0 y b minus plus b 1 y dot b is equal to beta. So, this is the BVP, call it 1a 1b, and the corresponding initial value problem. So, u double dot equal to f of t u dot and a 0 u a minus a 1 u dot a is equal to alpha and c 0 u a minus c 1 u dot a equal to s. Okay, and we are normalizing. So, a 1 c 0 minus a 0 c 1 is 1. Okay, so, normalizing that, and we are calling the solution u, stressing the importance on the dependence of s, and then we found this function coming from the second boundary condition b 0 u b s plus b 1 u dot b s minus beta, and whenever there is a root of, so if phi s star is 0, then y t defined by, so this is definition u of t s star solves BVP 1. Okay. And if there are more roots, then we will also have more solutions for the BV problem, and this follows from uniqueness of the initial value problem. Okay. So, the important thing is this. So, we are stated the theorem using the global Lipschitzness of f. So, we have existence and uniqueness. So, later on we also need continuous dependence on this solution. We are going to differentiate with respect to s, and as of now, so existence and uniqueness results of IVP are giving us the solutions of the boundary value problem, provided this function phi has roots. If this has no roots, then we are, by this method we are not able to produce any solutions of the BVP. Okay. So, that is so you can imagine if we go to higher order equations or even first order systems. So, this phi, so remember here the phi is from R to R, okay, and soon we will state a result where existence of roots is guaranteed, conditions on phi. So, if you go to higher order equations or more general first order systems of first order equations, then this phi will be a mapping from some Euclidean space to some other Euclidean space, and the study of its zeros, existence of its zeros becomes more complicated, and that is where you need the tools from non-linear analysis. In this one dimensional case, we can do all that thing just using one dimensional calculus, and that is what we are going to do. So, let me just state a result, and we will discuss in more detail next time. So, just I will just write a theorem. In addition to the hypothesis of global Lipschitz etc. So, we have also several conditions on the coefficients etc. Assume, so this is some extra assumptions on the non-linear right hand side. So, del f by, so remember f of t u1 u2. So, that is the right hand function. Okay. So, del f 0 and del f by u2 bounded. Okay. And so, A0 A1 non negative product, B0 B1 non negative, and A0 and B0 do not vanish simultaneously. So, this is the condition. So, this means A0 A1 are of the same sign. And similarly B0 B1 and A0 B0 do not vanish simultaneously. So, this is the condition. Then BVP has a unique solution. Okay. So, we will prove this theorem because it is quite interesting, bit technical, but it uses only one dimensional calculus. So, the idea of the proof is, let me just state that idea of the proof. So, look at this phi again from R to R, okay, and show that phi has a unique root. S star, that is phi of S star is 0, and there is no other S for which phi vanishes. So, even in one dimensional case, okay, we have of course several conditions. So, one of the conditions to have such a result in one dimensional case is to show that this phi is a function of S. Okay. So, you show that d phi by ds, okay, next time we will do that, d phi by ds is bounded away from 0. Okay. So, this is one sufficient condition under which this is true, and what we are aiming at, these conditions, additional conditions on f and also on the coefficients, okay, ensure this. Okay, that is what we use one dimensional calculus using this hypothesis to show that this d phi by d s is bounded away from 0, and then the calculus lemma will give us the unique root satisfying this thing, and that will prove that BVP has a unique solution. So, we will see next time. Thank you.